In this video, we're going to go over some practice problems on electrochemistry. Now, for each of these problems, I recommend that you pause the video and work on them yourself. So let's start with this one. Number 1. Which of the following statements is false? Oxidation always occurs at the anode. Is that true or false? That is a true statement. Oxidation will always occur at the anode. Reduction occurs at the cathode. Oxidation involves a loss of electrons, and reduction involves a gain of electrons. Now what about B? Electrons always flow from the anode to the cathode. That is a true statement. And C, the salt bridge is used to maintain charge balance. That is also true. D, a galvanic cell may have a negative or a positive cell potential. True or false? Now that is a false statement. A galvanic cell may have a positive potential or a cell potential of 0, never negative. An electrolytic cell can have a negative cell potential. So D is the answer. And E, cations always flow toward the cathode, that's true, and anions flow towards the anode. Number 2, sketch a galvanic cell based on the following standard reduction potentials. Identify the anode, cathode, and the salt bridge. Determine the direction of the electron flow. Write the overall balance reaction, the standard line notation, and calculate the net cell potential. Now, due to limited space on the screen, I'm going to start with the cell potential first, and the overall balance reaction. Now we have a galvanic cell, so the overall cell potential, it must be positive or 0. It can't be negative. So we need to adjust the directions of these half cell reactions. So for one thing, we can't have the electrons on the same side. One has to be on the left, one has to be on the right. Basically, one of the half reactions has to correspond to oxidation, and the other has to correspond to reduction. So we need to reverse one of the half reactions. The question is, which one? Now we need to do it in such a way that when we add up the cell potentials, we need to get a positive cell potential. So if we reverse the first one, it's going to be positive 0.23. And if you add that to negative 0.76, that will still be a negative cell potential. So therefore, you want to reverse the reaction that has the highest or most negative cell potential, which is the first one. So let's rewrite this. So I'm going to reverse the first reaction, and I'm going to leave the second one exactly the way it is. So now the cell potential for this reaction is positive 0.76. If you multiply the reaction by 2, the cell potential will not change. All you can do is reverse it. Now let's leave the second one exactly the way it is. And so the cell potential for this is going to stay negative 0.23 volts. Now, once the electrons are on opposite sides, we can add the two reactions. And so notice that the electrons will cancel. And so this is going to be zinc plus nickel 2 plus. And this is going to produce nickel metal. These are in the solid phase. And then zinc 2 plus. All of the ions are in the aqueous phase. So just keep that in mind. Now the overall cell potential is going to be the sum of these two numbers. So 0.76 plus a negative 0.23, that's going to give us a cell potential of positive 0.53 volts. So this is one of the answers. That's the net cell potential, and this is the overall balanced reaction. Now let's identify the anode and the cathode. So how can we do that? What's the anode and what's the cathode in this example? Now oxidation always occurs at the anode, and reduction occurs at the cathode. So which one of these two half reactions represent the anode and which one is associated with the cathode? So here's a quick way to tell. If the electrons are on the right side, that half reaction is associated with the anode. If the electrons are on the left side, that half reaction will be associated with the cathode. Oxidation always occurs at the anode. Reduction always occurs at the cathode. So if we look at zinc, it's losing electrons. Oxidation is associated with a loss of electrons. The nickel plus 2 ion, or 2 plus ion, is gaining electrons, and so that's associated with reduction. Now, oxidation is also associated with an increase in oxidation state. Reduction is associated with a decrease in oxidation state. The oxidation state of any pure element in its natural state is 0. So going from zinc to zinc 2 plus, going from 0 to 2, it increases. And so zinc is being oxidized. Therefore, zinc metal is the anode. Now, nickel 2 plus is going from 2 to 0. So the oxidation number is decreasing. So nickel 2 plus is being reduced, which means that nickel metal is the cathode. So the anode is zinc metal, the cathode is nickel metal. Now let's go ahead and take a minute and sketch the galvanic cell. So I'm going to have two beakers separated from each other. And in the first one, I'm going to draw an electrode. In the second one, I'm going to draw another electrode. Now I'm going to connect a wire between the two electrodes. And if you want, you could put something in between, like a voltmeter or something, or a light bulb. But that's not necessary. You could do that if you want to. And then we need to have the salt bridge. But first, let's put some fluid in both containers. Now the salt bridge is just going to be represented by this line. It's to maintain charge balance. So I'm going to use this as zinc metal, and this is going to be nickel metal. So therefore this, on the left side, represents the anode. And on the right side, this is the cathode. Now I'm going to use a solution of zinc sulfate. And on this side, I'm going to use nickel sulfate. Now I'm going to choose a standard concentration value, and that is a 1 molar solution. If the concentration is not standard, then the cell potential will deviate from 0.53. Right now, the standard cell potential is positive 0.53 volts. Now, this little symbol here indicates that this is the standard cell potential, which means the concentration of zinc 2 plus and nickel 2 plus is 1 mole per liter. But if we change that concentration, then this value will change slightly. So if you increase the reactant, nickel 2 plus is a reactant in the overall cell potential. If you increase the reactant, the reaction will drive to the right, and so the cell potential will increase. If you increase a product like zinc 2 plus, then the cell potential will decrease. Think of chemical kinetics. If you increase the reactants, the reaction will speed up. And it's kind of similar to that. If you increase the reactants, it's going to shift to the right, and that's going to increase the cell potential. If you increase the products, it shifts to the left, so that will decrease the forward cell potential. So just some things to keep in mind. Now let's get back to this problem. Now electrons will always flow from the anode to the cathode. So they're flowing in this direction. Now, as zinc gives away electrons, it's going to turn into the zinc 2 plus ion. So as the zinc atoms give up their electrons, this zinc atom is going to go into the solution as zinc 2 plus. So I'm just going to draw zinc 2 plus here and put an arrow. So notice that the anode is losing mass, and the cathode gains mass. So as the electrons enter the cathode, the nickel 2 plus ions in a solution will be attracted to these negatively charged particles, and so they will accelerate towards the cathode. As the nickel 2 plus ions reach the cathode, they will acquire electrons, turning into nickel metal, and so they will deposit themselves on the cathode. And that's why the cathode gains mass, but the anode, it loses mass. Now, as we mentioned before, this is the salt bridge. In the salt bridge, the cations will flow towards the cathode. So the zinc 2 plus ions, as they flow into the solution, they're going to travel this way through the cathode and eventually go this way, because they too are attracted to the electrons in the cathode. However, the nickel 2 plus ions, they will have a stronger affinity for these electrons than the zinc 2 plus ions. So until all of the nickel 2 plus ions get to the cathode, none of the zinc ions will go on it, but they will be attracted to it. So they're going to travel in that direction because they do have a positive charge. So the cations will flow towards the cathode. The anions, which basically represent sulfate, anions have negative charges. Anions are attracted to the anode. So in a salt bridge, they will feel a force that will accelerate them in the opposite direction, towards the anode. So we've covered almost everything. We've identified the anode, cathode, salt bridge. We've sketched a galvanic cell. We have determined the direction of the electron flow. The only thing that we need to do is write the standard line notation. So how can we do that? The basic setup for a cell notation looks like this. So first you want to start with the anode material, which is typically a solid metal, and then you want to use a vertical line to separate from one face from another. So this is in a solid phase, and then you can have this stuff in the aqueous phase. So every time the phase changes, use a vertical line. Now you need a double line to separate the oxidation half cell from the reduction half cell. And then we're going to have other stuff in the aqueous phase, and then another line, and then the cathode material. Now sometimes you may have a gas and something in the aqueous phase. So what you could do is you can write the stuff in the gas phase, and then a line, then the stuff in the aqueous phase, and then another line, and then the cathode material, which is in the solid phase. So that's possible as well. Now for this particular example, the anode is zinc metal, and then we need a vertical line. Now in the aqueous phase, we have the zinc 2 plus ion, and the concentration of that ion is 1m, 1 mole per liter. And then on the right we have the nickel 2 plus ion in the aqueous phase, and it has the same concentration of 1 mole per liter. And then the cathode is nickel metal. So that's a simple way in which you can write the standard line notation or cell notation of a galvanic cell. Now, if you want more examples on writing cell notations, you can look at my video entitled Cell Notation Practice Problems on YouTube if you want more examples on this, particularly harder examples. Now let's work on another problem that's similar to the last one. So go ahead and pause the video and do everything that we did in the last problem. So I'm going to start with the overall balanced reaction. So for a galvanic cell, the net cell potential has to be positive. If I reverse the first reaction, then I'll have two values that are negative, and so that will not be positive. Therefore, I have to reverse this reaction. Now the second thing I need to do is multiply this reaction by 3, because the number of electrons must be equal when adding the two half reactions. So the first reaction will be as follows. So I'm just going to reverse the first reaction. So the cell potential for this reaction is going to change from negative to positive 1.66 volts. Now I'm going to multiply this one by 3. the number of electrons must be equal in order for this to work. So I'm going to have 3 electrons this time in both half reactions. Now the cell potential will not change. Do not multiply that by 3. That's going to stay the same, positive 1.82 volts. So now we can add up the 2 half reactions. So we can see that the number of electrons will cancel, and so the overall balance reaction will be solid aluminum plus the 3 cobalt ions in the aqueous phase, and then that's going to turn into this stuff plus the aluminum cation, which is also in the aqueous phase. Now the net cell potential will be the sum of these 2 values. So 1.66 plus 1.82, that's 3.48 volts. So that is the standard cell potential for this particular galvanic cell. Now we need to identify the anode and the cathode. So which half reaction is associated with the anode and which one is associated with the cathode? Well, anytime the electrons are on the right side, we know that that reaction is going to be associated with the anode. Anytime you have electrons on the right side, it's an oxidation half reaction. And as you can see, the oxidation state goes from 0 to 3. So therefore the oxidation number increases. So this is an oxidation half reaction. And plus we have the loss of 3 electrons. If the electrons are on the right side, then that tells us that aluminum is losing electrons. Now this half reaction is associated with the cathode because the electrons are on the left side. And so you can see the oxidation state decreasing from 3 to 2. If the oxidation state goes down, it's reduction. So now that we know which one is the anode and which one is the cathode, we can draw a galvanic cell. So this is going to be the first electrode, and here we have the second electrode. And let's put a wire in between them. So I'm going to choose this as, let's do this first. Let's make this electrode aluminum. And what should be the other electrode? Because we didn't have cobalt metal or solid cobalt in the overall balance reaction. So because cobalt was not in its metallic form, we need to use another electrode, an inert electrode. You can use graphite, which is a carbon-based electrode, or you could use platinum. I'm going to use platinum in this case. So this is the anode, and this is the cathode. Now keep in mind, electrons always flow from the anode to the cathode. Now in this half cell, I'm going to put aluminum chloride, and it's going to be a 1 molar solution. And in this one, I need to use cobalt chloride, that's cobalt 3 chloride, which is 1 molar, and also cobalt 2 chloride, which is also going to be 1 molar because I need to have both ions, the 2 plus ion and the cobalt 3 plus ion in that solution with the same standard concentration. And let's not forget the salt bridge. So as we said before, cations, like the aluminum 3 plus cation, will flow towards the cathode, and anions, in this case chloride, will flow towards the anode. So this is the half reaction that's associated with the anode. And this is the half reaction associated with the cathode. Now the last thing that we need to do is write the standard line notation or cell notation. So we're going to start with the anode material. That's aluminum metal. And then we need a vertical line to change from the solid phase to the aqueous phase. And so in the aqueous phase, we have the aluminum 3+ cation with a concentration of 1 m. Now, we need a double vertical line to separate from the anode half reaction and the cathode half reaction. So now, on the cathode side, we have two things that are part of the reaction and in the aqueous phase. So we're going to have a cobalt 3+ with a concentration of 1 m, and then a comma to separate it from the other one, cobalt 2+ with a concentration of 1 m as well. And then we need a vertical line, and then we need to write the cathode material, which is platinum metal. So that's the cell notation for this example. Number 4. Calculate the Gibbs free energy change for the reaction shown below at 25 degrees Celsius. So what formula do we need to calculate delta G? Delta G is equal to negative NF times the cell potential. Now first we need to calculate N, and we need to write the overall reaction in terms of half reactions. So zinc turns into the zinc cation by releasing 2 electrons, and the copper 2+ cation needs to acquire those 2 electrons to turn into copper. So the number of electrons in the balanced overall reaction is equal to N. So N represents 2 moles of electrons. So now that we have that, we can calculate the cell potential. So we have 2 moles of electrons. F is Faraday's constant, which is 96,485 coulombs per mole of electrons. And the cell potential, it's 1.1 volts. And you need to know that 1 volt is equal to 1 joule per coulomb. Coulomb is the unit of charge. So we have 1.1 joule per coulomb. So we could cancel the unit coulombs and moles of electrons. So let's multiply these numbers to get the answer. So delta G is going to be equal to negative 212,267 joules. Now, if you divide it by 1,000, you can convert joules into kilojoules. So you could say this is approximately negative 212 kilojoules. And so that's the answer. Now let's move on to part B. What is the value of the equilibrium constant K? It turns out that delta G is also equal to negative RT ln K. So what we need to do is set these two equal to each other. So let's solve for K. Let's divide both sides by negative RT. On the right side, these two will cancel. On the left, the negative sign will cancel. So we have the natural log of K is equal to NF times the cell potential over RT. Now we need to convert this logarithmic equation into an exponential equation. And let me give you an example. Let's say if we have log base A of B is equal to C. A raised to the C is equal to B. And so that's how we can convert a logarithmic equation into an exponential one. I really don't need this reaction anymore, so I'm just going to get rid of that. Just keep in mind the cell potential is 1.1 volts and N is equal to 2. So now this is base E. So E raised to everything on that side is equal to K. So we could say that K is equal to E, which is the inverse of the natural log function, raised to the NF times the cell potential divided by RT. So now we have the equilibrium constant K in terms of the cell potential. So we know N is 2, F is 96,485, the cell potential is 1.1 volts, R is 8.3145, and T is 298 Kelvin. is 25 plus 273. So go ahead and plug that into your calculator and see what answer you get. So I got 1.607 times 10 to the 37. So that's the value of K. That's the answer. Number 5. The equilibrium constant K is 2.11 times 10 to the 91 for the reaction shown below at 25 degrees Celsius. Calculate the standard cell potential for that reaction. So let's start with these two equations once more. And let's set negative NFE equal to negative RT ln K. So this time, we need to solve for this cell potential. And so I'm going to divide both sides by negative NF. So on the right side, these two will cancel. On the left side, it will just be the negative sign. So the cell potential is RT natural log of K divided by NF. Now, we need to calculate N. So let's separate the overall reaction into half reactions. As aluminum turns into the aluminum 3+ cation, it has to give away 3 electrons. Now we have a 2 in front of Al, so we got to multiply that reaction by 2. And 2 times 3 electrons is 6 electrons. Now, the zinc 2+ cation has to acquire 2 electrons to turn into zinc metal. And we have a 3 in front of it, so 3 times 2 electrons is also 6 electrons. So the number of electrons in the balanced overall reaction is equal to N. So N is 6 in this example. So R is 8.3145. The temperature is 25 plus 273, so that's 298 Kelvin, times the natural log of the equilibrium constant, divided by N, which is 6, times Faraday's constant, 96,485. So the cell potential in this problem is 0.9 volts. So this is the answer in part A. So now let's move on to part B. What is the maximum amount of work that can be obtained if 8 moles of aluminum reacts with excess zinc 2+? Now what you need to know is that the maximum work obtained is equal to delta G. And delta G, we know it's negative NFE. So N, we saw that it's 6 moles of electrons. Faraday's constant, 96,485 coulombs per mole of electrons. And the cell potential, which is 0.9 volts, that's 0.9 joules per coulomb. So we could cancel the moles of electrons, and we can cancel the unit coulombs. So it's going to be negative 6 times 96,485 times 0.9. And so delta G is equal to negative 521,019 joules. Now let's convert that to kilojoules by dividing it by 1,000. And I'm going to round it. So this is approximately equal to negative 521 kilojoules. And so that value for delta G corresponds to this reaction. So I'm going to write that here. Now here's a question for you. What happens if we multiply that reaction by 2? What happens to delta G and the cell potential of this reaction? So if you multiply that reaction by 2, this will increase by a factor of 2. So it's going to be negative 1,042 kilojoules. So this corresponds to 4 moles of aluminum and this value corresponds to 2 moles of aluminum. So if we want the delta G value per 1 mole of aluminum, it's going to be 521 divided by 2. So just keep that in mind. Now the cell potential will not change. If you multiply the reaction by 2, it's going to remain 0.9. So that's another thing that you want to keep in mind as well. So now let's finish this problem. What is the maximum amount of work that can be obtained if 8 moles of aluminum reacts? If 2 moles react, 521 kilojoules of work can be obtained. So if 8 moles react, we got to multiply this by 4. So that's going to be like 2084. So here's how you can set it up. Start with 8 moles of aluminum, the limiting reactant. This is the excess reactant, so we don't have to take that into consideration. Now, for every 2 moles of aluminum that reacts, 521 kilojoules of work can be obtained. So it's going to be 8 divided by 2, which is 4, times negative 521. And so the maximum work is negative 2084 kilojoules. And so that's delta G if 8 moles of aluminum reacts. Number 6. Which of the following statements is true? Oxidation is associated with a decrease in oxidation number, and it occurs at the cathode. That is a false statement. Oxidation is always associated with the anode. Reduction occurs at the cathode. And during oxidation, the oxidation number increases. For reduction, the oxidation number decreases. And oxidation is always associated with a loss of electrons. Now what about B? Increase in the mass of the anode will increase the cell potential. And that's false. The anode is a solid, and increase in the solid will not change the position of equilibrium. It's not going to affect the cell potential. So B is out. Now if you change the concentration of the reactants dissolved in the solution, that will change the cell potential. Part C. Increase in the concentration of the reactant ions will increase the cell potential. That is true. If the reactant ions increase in concentration, the cell potential will go up. If you increase the product ions, the cell potential will go down. So C is the answer. D, the cell potential is positive when delta G is positive. That's a false statement. So let's make a table between the cell potential, delta G, and K. When delta G is positive, when the cell potential is positive, delta G is negative, and K is going to be very large. And so what you have is a spontaneous process, a reaction that is product favored. Now, if the cell potential is 0, delta G will be 0, and so K is equal to 1, and the reaction is in equilibrium. If the cell potential is negative, delta G will be positive. K is going to be less than 1, but K is never negative, so K is going to be between 0 and 1. So K is small. And so this is going to be a non-spontaneous process in the forward direction. So thus we can see why D is a false statement. The cell potential is positive when delta G is positive. That's not true. The cell potential is positive when delta G is negative. Now what about E? Is that a true or false statement? The cell potential is positive when K is very large. And that is true. When the cell potential is positive, K is greater than 1. So we have 2 true statements. So there's 2 answers. Answer choice C and E are both true. Number 7. The standard cell potential for the overall balanced reaction shown below is 1.07 volts. The concentrations of copper 2 plus and chromium 3 plus are 2.4 and 0.05 moles per liter respectively. Will the cell potential be higher or lower than 1.07 volts? So notice that the amount of reactant ions is significantly greater than the amount of product ions. And as we mentioned before, if you increase the reactant ions, the cell potential will increase. If you increase the product ions, the cell potential will decrease. So since the reactant ions are much greater in concentration than the product ions, the cell potential of the reaction should be greater than the standard cell potential. So I'm going to say that it's going to be higher than 1.07. So we're going to see if that's true. Let's go ahead and calculate that. So we need to use the Nernst equation in order to calculate the cell potential under non-standard conditions. If the concentration of the ions are not 1 mole per liter, then the conditions are non-standard. So we're going to use this equation. The cell potential is going to be equal to the standard cell potential minus 0.0591 times log Q divided by N. So this is assuming the temperature is standard. And since nothing was specified about the temperature, we're going to assume that the temperature is the standard temperature of 25 degrees Celsius or 298 Kelvin. Now in part C, the temperature is 40 degrees Celsius. So we need to use a different form of that equation for that part. Now first, let's focus on N. So notice that we have 2 chromium atoms. How many electrons do we need to balance this reaction? The total charge on the left side is 0. On the right side, it's 2 times 3 plus, or plus 6. So we need 6 electrons to balance that reaction. And then if we focus on copper, on the right side, the charge is 0. On the left, it's plus 6. So we need 6 electrons on the left to balance it. So we can clearly see that N is equal to 6 for this particular problem. Now what we need to do is calculate Q, the reaction quotient. Now the way you calculate Q is very similar to calculating K. It's products over reactants. Now we can't use anything in the solid state, only the stuff in the aqueous state or the gaseous state. So chromium 3 plus is in the aqueous state and it has a coefficient of 2, so we need to square it. Copper 2 plus is also in the aqueous state, but the coefficient is 3. So K and Q would both be equal to this. The only difference is that for K you're using equilibrium concentration values, and for Q you're using initial concentration values. So the initial concentration of chromium 3 plus is 0.05. And the initial concentration of copper 2 plus is 2.4. So if we plug that in, this is going to be 1.808 times 10 to the negative 4. So that's Q. So now let's plug in everything into the Nernst equation. So the standard cell potential, that's 1.07, and then minus 0.0591 log Q, and then we're going to divide that by N, and we saw that N is equal to 6. So go ahead and type all of that in. So I got 1.107 volts. So notice that the cell potential went up. It's greater than 1.07. It's 1.1. Or you can round that and say it's 1.11. So the cell potential is greater than the standard cell potential. Why? Because the amount of reactant ions is greater than the amount of product ions. So if you increase the reactant ions, relative to the product ions, the cell potential will increase. If you increase the product ions relative to the reactant ions, the cell potential will decrease. So make sure you understand that. So now that we have the answer to part B, let's move on to part C. But first, let's get rid of some stuff. If the cell potential was 1.02 at 40 degrees Celsius, and the concentration of copper 2 plus is 0.24, what is the concentration of copper 3 plus? So now we need to use the other form of the Nernst equation. So the non-standard cell potential is equal to the standard cell potential minus RT divided by NF times the natural log of Q. Now we need to calculate Q if we're going to calculate chromium 3 plus. So let's isolate Q. Now the first thing I'm going to do is I'm going to take this term, move it to this side. So it's negative on the right, but it's going to be positive on the left side. And then I'm going to take this, move it to that side. It's positive on the left, but it's going to be negative on the right. So now I have this equation. And then I'm going to multiply both sides by the reciprocal of this fraction. That is by NF over RT. So multiplying these two, we can see that NF will cancel and RT will cancel. So on the left, I'm just going to have the natural log of Q. On the right, I'm going to have the difference between these two cell potentials multiplied by NF divided by RT. So now, this is base E. So I'm going to convert this equation to its exponential form. So E raised to everything on that side is equal to Q. Or we could say that Q is equal to E raised to the difference between the cell potentials times NF divided by RT. So let's go ahead and calculate Q, the reaction quotient. So the standard cell potential is 1.07. The actual or non-standard cell potential is 1.02. And then N in this problem is 6. Faraday's constant is 96,485. And divided by RT, which is 8.3145. Now, if the temperature was 25, we could have used the other form. That is this form. It was, what was that equation? It was E is equal to standard E minus 0.0591 log Q over N. So if the temperature was 25 degrees Celsius, we could just isolate Q in this one. But if the temperature is different, then you need to use the other form, which is basically this form. So we need the Kelvin temperature. Let's add 273 to 40. 40 plus 273, that's 313 Kelvin. So go ahead and type all this in. So I got 67,673.7. So that's equal to Q. And we know that Q is the ratio of the product ions to the reactant ions. And this is going to be raised to the third power based on this coefficient. So let me get rid of this stuff here. So this is Q, and that's equal to CR3 plus squared, which at this point we can call it X squared, since that's what we're looking for. and the concentration of copper is 0.24, and that's raised to the third power. So let's cross multiply. 1 times x squared is x squared. And then we're going to have 67,673.7 times 0.24 raised to the third power. And that's about 935.5. So now let's take the square root of both sides. So x, which is represented by the concentration of chromium 3+, that's equal to 30.6 m, which is pretty high. But that should be the concentration of chromium in order to get a cell potential of 1.02, given the cell potential of copper 2+. So that's it for this problem. Now, for those of you who want more practice problems on the Nernst equation, I have a video on YouTube. Just search Nernst equation Organic Chemistry Tutor, and it should come up. So let's focus on number 8. What mass of chromium metal can be plated on the cathode from a chromium 3 chloride solution given the current of 5.8 amps and it's active for a time of 12 minutes? So how can we solve this electroplating problem? Well, there's some things that you need to know. And you need to know that charge is equal to current multiplied by time. The unit of charge is the coulomb, and the unit of electric current is the amp. So 1 coulomb is 1 amp times 1 second. And recall that Faraday's constant is 96,485 coulombs per mole of electrons. And so this unit, understanding it, is going to be important for solving these types of problems. So let's go ahead and begin. Let's calculate the charge that passes through the solution, or that's used to plate chromium onto the cathode. So first I'm going to start with the time in minutes. So we have 12 minutes, and we need to convert minutes to seconds. So 1 minute is 60 seconds. Now once we multiply the time in seconds by the current in amps, we can get the charge in coulombs. So let's multiply this by the current in amps. So right now the unit minutes cancel. And we know that 1 coulomb is 1 amp times 1 second. So we could cancel the unit amps and the unit seconds. So now we have the charge in coulombs. And now we can use Faraday's constant, which is 96,485 coulombs of charge, and that equates to 1 mole of electrons. Now once you have the moles of electrons, you can convert that to the moles of substance. Now we have a chromium 3+ solution, or chromium 3 chloride solution, which means the chromium 3+ ion is in it, and 3 electrons are required to reduce it to chromium metal. So the molar ratio between the chromium substance and the number of electrons is 1 to 3. So we could say that 1 mole of chromium will be reduced or plated on a metal if 3 moles of electrons passes through the wires of the cell. At this point, we can convert moles to grams. So we need the periodic table, and the molar mass of chromium is about 52 grams per 1 mole. And so that's how you can calculate the mass that will be plated. You could just do a simple conversion. So these will cancel, and these units will cancel as well. So it's going to be 12 times 60 times 5.8 divided by 96,485 divided by 3, and then times 52. So 0.75 grams of chromium will be plated on the cathode. So that's the answer. Number 9. How much current is needed to plate 12 grams of iron metal on the cathode using an iron 2 sulfate solution in 4 hours. So let's calculate N first. So the Fe2 plus ion is present in iron 2 sulfate, and so 2 electrons are required to reduce it to the metal. So we can see that N is 2, which means there's 2 moles of electrons per 1 mole of Fe. So now, if we're given a mass, how can we calculate the current? My recommendation is to start with the mass. So we have 12 grams of iron metal, and then convert it to moles using the molar mass. So the molar mass of Fe is about 55.85 grams per mole. So 1 mole is 55.85 grams. Now, once we have the moles of the substance, we can convert it to the moles of the electrons. So for every 1 mole of Fe that's plated on the cathode, 2 moles of electrons was used in the wires of the galvanic cell or the electrolytic cell. So we could cancel out grams of Fe at this point and moles of Fe. Now, once we have the moles of electrons, we can convert that into coulombs. 1 mole of electrons is equal to 96,485 coulombs. And keep in mind, 1 coulomb is 1 amp times 1 second. So to get the current in amps, we need to divide by the time in seconds. So first, let's divide by the number of hours, and then convert hours into seconds. So 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. So we could see that the unit hours cancel, and the unit minutes cancel. Let me use a different color for that. And so the unit seconds will now cancel as well. And then also we can see that coulombs cancel. And there's one more unit that cancels. It's moles of electrons. So the only unit that we have left over is the amps, which is what we want. That's the unit for current. So this will give us the answer. It's 12 divided by 55.85, and then times 2 times 96,485, divided by 4, divided by 60, and divided by 60 again. So the current is 2.88 amps. And that's the answer to this problem. Now, if you want to get more questions like this, there's a video I created on YouTube. If you type in electrolysis and electroplating problems, organic chemistry tutor, it should come up. So feel free to check that out if you want more examples on these types of problems. So thanks again for watching, and have a good day.